So to get started, let's see what hydrolysis is all about. So first of all, we have to define what hydrolysis is. When neutral ionic compounds are dissolved in water, some of these ions do tend to change the pH of the solution. In some cases, the pH decreases, and in some cases, the pH increases. This is what normally happens. Now, this is caused due to hydrolysis. Now, if the salt produces an acidic solution, it is an acid hydrolysis. If the solution becomes basic, then we have basic hydrolysis. So it is the interaction of water with certain ions that are present in water that causes hydrolysis to take place. And we need to be able to predict which compounds will actually bring about hydrolysis. That is something that we really want to see, okay? Now, one of the typical questions that you will get will look something like this. By the end of the lesson, we will actually answer this question, but here is a question just to get a feel of what to expect. Will adding ionic salts to water change the pH of water? We are merely asking, will there be hydrolysis? Now, the question that we normally pose is with an example. So if you add table salt to water, will it change the pH? Ammonium chloride, if you add to water, will it change the pH? Sodium acetate, if you add to water, will it change the pH? Ammonium acetate. Now, these are 4 examples that I've picked, and then we will go with each of these, and we will explain how we can predict qualitatively whether there will be a change in pH. That is one of the things that we have to do today. And then we also have to answer certain questions like you had in your previous assignment, where you had to calculate the pH of certain ionic compounds. So we can do both. So we are going to use the concept of hydrolysis in explaining the 4 questions, the 4 examples that has been cited, okay? Now, the first thing that you need to recognize is what ions can actually cause hydrolysis. Now, we should be able to come up with answers for this because we did get introduced to the concept of acids and bases, and we talked about strong acids, strong bases, weak acids, and weak bases. So if you know the different examples of strong acids and weak acids, you should be able to answer the following questions as we go along, okay? So here we're going to use the word strong conjugate bases, or SCB, and strong conjugate acids, SCA for short, we tend to write like that, cause the pH of aqueous ionic solutions to change. So this is what we're looking for. If you take an ionic compound and dissolve it in water, it forms positive ions and negative ions. The positive ions and negative ions, are they strong conjugate acids or strong conjugate bases? If you know the answer to that question, you can predict what would be the change in pH. Does it make sense? So you're going to add an ionic compound to water, and you're going to predict whether the pH is going to change. So we're using the words like strong conjugate base and strong conjugate acid. Now, when we talked about Bronsted-Lowry theory, we talked about acids, bases, conjugate acids, and conjugate bases. Now, we're going to clearly define the products, strong conjugate acid and strong conjugate base, which are actually the products of ionization based on the Bronsted-Lowry theory. So if you can write a dissociation or an interaction of water with acids, you get conjugate acids, conjugate bases, and we can identify them as strong conjugate acids and strong conjugate bases, depending upon what type of acid is actually involved. Now, the next statement says these ions can come from ionic compounds or salts. So any ionic salt or ionic compound dissolved in water. Now, every time we talk about the word salt, one of the common examples that comes to your mind is table salt. In reality, when we talk about salts, we imply any ionic compound that can be formed by a neutralization reaction. So if you have neutralization reactions, then we can actually, if you know what neutralization reactions are, the products that are obtained for any kind of neutralization reaction is salt and water. The salt could be different ionic compounds. These are usually spectator ions that are soluble in water. Okay, so we are going to identify them as weak acids, weak bases, and then look at the conjugate acids and conjugate bases. That's what we're going to do here. Okay. What are strong conjugate bases? You have to be very clear about what I'm saying. Make a mental note of it. You need to identify a strong conjugate base. The conjugate bases of weak acids. I said you could memorize a list of acids and bases, either of strong acids or of weak acids. Strong acids are lesser in number. We did write down 6 examples of strong acids. We did HCl, we had HNO3, H2SO4, HClO4, and then we did HCl, HBr, and HI. I repeated the halogen acids here. So these are all strong acids, and I said there are 6 examples of them. So if you look at these 6 examples, these are not weak acids. So we will not be looking at nitrate, sulfate, perchlorate, chloride, bromide, and iodide. We are looking for strong weak conjugate bases. Weak conjugate base, sorry, I'm talking about weak acids producing strong conjugate bases. So if I take an acid like this, HC2H3O2, this is not in this list. So I'm going to call it a weak acid. Okay, so that's how we will be going about. We want to identify weak acids. So we go to this list that we have already made. And if the example given is not on this list, then we call it a weak acid. So if you take this acid, which is actually nothing but acetic acid, this can also be written as CH3COOH because it's a carboxylic acid. So if you dissolve it in water, it actually changes into so if you apply the Bronsted-Lowry concept, this is the acid, this is the base, this is the conjugate acid, and this is the conjugate base. Okay, so when you have a weak acid and when it undergoes interaction with water, the products form conjugate acids and conjugate base. The conjugate base that comes from a weak acid is always called a strong conjugate base. So you need to be able to identify an ion that is present in water, irrespective of where it comes from. Doesn't matter. As long as you have an acetate ion in water, that will be considered a strong conjugate base because the acetate ion is coming from acetic acid. Acetic acid is a weak acid. Weak acids produce strong conjugate base. This has to be the reality. Okay. So that's why I said you have to memorize the list of strong acids. So I'm going to write another example here. HCN. Is it a strong acid or a weak acid? Can you type your answer? HCN is a weak acid because HCN is not on the list. So when we allow HCN to interact with water, it's going to produce H3O plus Cn minus. So this is the acid, this is the base, this will be the conjugate acid, this will be the conjugate base. Now the question is Cn minus a strong conjugate base or a weak conjugate base? So this is a weak acid, therefore this will be a strong conjugate base. Does it make sense? So we can easily identify strong conjugate bases, and only then we can talk about hydrolysis. So it doesn't matter where the Cn minus or the acetate ion comes from. If you do have any of these ions in water, it is actually a strong conjugate base. Now, let's erase this and come back. this reaction, this is an acid, this is a base, this is a salt, and this is water. So every time you have a neutralization reaction between an acid and a base, it produces a salt. In this case, it is NaCN. So let's say I got a beaker of water. I got water in here, and into that, I'm going to put NaCN. So now in this water, I have Na positive and Cn minus. The question is Cn minus, what kind of base is it? You have to identify this as a strong conjugate base. It's not coming from an acid, it's coming from an ionic compound, which we can call as a salt. We are only adding NaCN, but now this water contains Cn minus. Because Cn minus is a strong conjugate base, it will undergo what we call hydrolysis. So does it make sense? So that's something that you got to identify right away. Every time I give you an ionic compound, you dissolve it in water. If it forms a negative ion, so strong conjugate bases or bases according to Bronsted-Lowry theory will always mean a negative ion. In this case, the Cn minus. So again, let's take a beaker, fill it with water, and I'm going to add NaCl. So I have Na plus and Cl minus. So Cl minus is a negative ion. It is a base. It's a conjugate base. The question is it a strong conjugate base or a weak conjugate base? Can you type in your answer, please? I like more of your answers. Now here we have both answers. I have students who have given me weak as well as strong. So the question is Cl minus is coming from NaCl. NaCl is a salt, and which acid and base did you use to prepare sodium chloride? So in this case, I'm using HCl. HCl is on this list. It is a strong acid. So the negative ion that is coming from a strong acid, what kind of base will it be? I need an answer. What kind of base will it be? Will it be a strong conjugate base or a weak conjugate base? It will be a weak conjugate base. That is what you have to identify. So if you look at nitrates, sulfates, perchlorates, chloride, bromide, iodide, they are always considered as weak conjugate bases, and they will not undergo hydrolysis. We can safely say that. So if the ionic compound that is given to you contains any other negative ion, which is not included in this list, it's 99% possible that it will undergo hydrolysis. So that is what we need to recognize. We need to recognize what we call a strong conjugate base, and we have learned how to do that. And with this, you can actually proceed into hydrolysis and say what exactly is hydrolysis and how does it change the pH. And that's what we are going to look at. Okay. So the first part is pretty straightforward. We use the strong acids list to identify the conjugate base that is produced using the interaction of the acid with water is referred to as conjugate acid and conjugate base, the products that are formed. Okay. So similarly, strong conjugate bases undergo hydrolysis. That is the important thing. So we know how to identify it. Then we can say that a strong conjugate base will undergo hydrolysis, and this is very important. So strong conjugate bases undergoes hydrolysis. So here is a reaction just to show how the strong conjugate base is formed. It can be formed either from an ionic salt or from an acid. So in this case, this is acetic acid that is formed that is interacting with water. I wrote this equation earlier. Now it's reinforcing here. So it produces hydronium ions plus acetate ions. Acetate ions are bases. Since it's coming from a weak acid, it's also a strong conjugate base. Okay, so this is a strong conjugate base. Okay, so that's what you have. So you should be able to label it. acid base, conjugate acid, and a strong conjugate base. So if you have a weak acid, if it dissolves in water, the negative ion that is formed is a base, and it will also be considered as a strong conjugate base. Strong conjugate acids, the complementary part. If the strong conjugate base came from a weak acid, a strong conjugate acid will come from a weak base. So one example that is commonly used for all of your problems, or in most of your problems, is ammonia and its derivatives. So you got to memorize that straightforward. If you see ammonium hydroxide, you see ammonium, or you see an organic compound which is attached to an NH2 group, they will all be basic in nature. Okay. So the conjugate acids of weak bases are called strong conjugate acids. Strong conjugate acids undergo hydrolysis, just like weak conjugate bases. This also undergoes hydrolysis. I'm going to write an example here. Ammonia, when dissolved in water, changes into ammonium ions and hydroxide ions. So ammonia, according to Bronsted-Lowry theory, will gain a proton, therefore it's a base. Water donates the proton, therefore it's an acid, producing a conjugate acid, which we are going to call a strong conjugate acid because this is a weak base. Okay, so when weak bases produce a positive ion, or you can say in solution, unlike the general definition of acids which should produce hydrogen ions, according to Bronsted-Lowry theory, all positive ions could be conjugate acids. And in this case, the conjugate acid is coming from a weak base. Therefore, it's referred to as a strong conjugate acid. Okay. Next, we will write hydrolysis and the representation of hydrolysis. So keep listening and relate to what I say. There are many ionic salts. Now, if I take HCl, the salt of HCl is NaCl. If I take HCN, the salt of HCN will be NaCN. Okay. If I take HC2H3O2, which is acetic acid, the salt of that would be NaC2H3O2. You will notice one thing. Here on the left, the first element is hydrogen. Therefore, they are all acids. Here on the right side, I have the salts. The first element is a metal. It need not be sodium. It could be potassium. It could be calcium. In spite of that, the product formed is a salt. You take an acid, replace the hydrogen with a metal, you get a salt. So when I talk about a salt, the salt is usually formed by taking the acid and replacing the hydrogen with a metal. That is another way of looking at it. So this happens when you have the neutralization reaction. Acid and base gives you salt and water. Okay, so those are some common things that you have already learned in grade 11 and grade 10. So we're just using that information, so it makes it easy. So when I say salt, now your understanding is it could be obtained from an acid by replacing its hydrogen ion or by a neutralization reaction. So there are many ionic salts that make aqueous solutions acidic or basic. Okay, that's what we're looking at. And we want to see how this happens, and we need to write equations for it. The reaction of ionic salts with water is called hydrolysis of salts. Okay, so we are redefining. So we are having an understanding of the concept of hydrolysis. We are talking about interaction of ionic compounds with water and how it's going to change the pH of water. So this is what I've been using, the Bronsted-Lowry theory. If the conjugate acid or base is a strong conjugate acid or a base, then there will be hydrolysis. Now, we have already learned how to identify a strong conjugate base and a strong conjugate acid. We have done that. So it's pretty simple and straightforward now. Weak acids and bases produce strong conjugate bases and strong conjugate acids. That is how we know that the negative ion formed is a strong conjugate base, or the positive ion formed is a strong conjugate acid, because it comes from a weak acid or a weak base. Next, we'll look at the illustration of hydrolysis. We're going to look at strong conjugate bases and strong conjugate acids. So here, A minus is a strong conjugate base. Like we talked about earlier, acids can be generally written as HA plus H2O, reversibly giving you H3O plus A minus. So this is the acid, this is base, conjugate acid, conjugate base. So A minus could be chloride, bromide, cyanide, it could be acetate, any one of these ions. So this is a general expression. So when I write A minus is a strong conjugate base, I'm using a generic equation to represent the acid. And if that is produced by the acid interacting with water, I can say A minus is a strong conjugate acid because this acid at this point of time is considered as a weak acid. Okay, so A minus is a base because it's negatively charged. And I'm saying it's a conjugate base because it was obtained from a weak acid. So if it interacts with water, A minus and H2O, if it interacts, water can actually change into H plus and OH negative. So together it is H2O. So this H plus will interact with A minus to give you HA. What remains would be the OH minus. So what happens is when A minus or a strong conjugate base interacts with water, it can attract the proton and form an undissociated acid. This acid is undissociated, therefore it will not show acidic property. If an acid has to show acidic property, it has to dissociate in water and form H positive ions. In this case, A minus is producing an undissociated molecule of an acid, and along with it is producing an ion which is OH minus. OH minus is a negatively charged ion, and this will increase the hydroxide ion concentration. Therefore, the pH of the solution will go up. The pH goes up when the hydroxide ions present in water goes up. So anytime you'd have a strong conjugate base, it can interact with water and produce hydroxide ions, thereby increasing the pH of the solution, or the solution will become basic. So now we can replace this. Okay, so let's see the next step. The dissociation constant, let's see. Okay, I just want to write a different example here. So I'm going to say Cn minus is a strong conjugate base. If it interacts with water, just like this, changes into HCN plus. The H is taken. So here you have H and OH, H plus, OH minus. This gives you OH minus, and this is going up, and therefore the pH will go up. So if I take NaCN, is an ionic compound, dissolve it in water, it produces Cn minus, interacts with water, produces undissociated HCN, and ions like OH minus is going to increase. Therefore, the pH of the solution will also increase. Does it make sense? So this is how the pH change occurs when you put an ionic compound in water, because there is the process of hydrolysis taking place between the strong conjugate base and water. Okay, so now it will be a little bit more clear. The dissociation constant for the hydrolysis in this case is referred to as Kb. As one of the products is a base, the pH goes up, therefore the solution will become basic. So I'm using this equation. So I'm writing an expression for the dissociation because this is an equilibrium expression. The products HA and OH, HA and OH. In the reactant, I will only use A minus because this is present in excess. This is a liquid that is present. I will not include it in the equation. Because the product is hydroxide, the subscript becomes B or Kb. Kb represents an equilibrium constant for any substance that produces a base. And usually, hydrolysis of salts in water, if you have strong conjugate bases, produce OH minus ion. Therefore, the equilibrium constant will be a Kb expression. On the other hand, if hydrolysis produces hydronium ions, then we have a Ka expression. So now what you need to recognize is, yesterday we talked about Ka and Kb for acids and bases, purely acids and bases. Today we are talking about hydrolysis, where acids and bases are not involved directly. We are putting ionic compounds in water, and then we are studying the pH of the solution. Sometimes it's going up, sometimes it's coming down. So this is what we have concluded based on all the experiments done, that every time we have the salt of a weak acid, the pH goes up because hydroxide ion goes up using this equation, and we can write an expression like this, which is called a Kb expression. On the other hand, if we have a strong conjugate acid, the opposite is also true, which we will see in a few minutes. Okay, so let's go to the next slide. Again, I'm taking a second example. I did one example, Cn minus. We are going to do an example with acetate ions, C2H3O2 minus. It's a strong conjugate base. Interacting with water, it produces undissociated acid. This is undissociated acid, and it produces hydroxide ions, which goes up. Therefore, the pH will also go up. The dissociation constant for the hydrolysis in this case is called Kb. And I want you to take a moment, and I want you to write the equilibrium constant expression. Okay, I want you to write the Kb expression for hydrolysis of acetate ions. Now, one of the questions that I see here is, why is water included in the equation? Just like when we write the equilibrium constant expressions where solids are not included, if one of the reactants is present in a very large excess, that is never included. So here, in this case, water is a reactant and also a medium in which the reaction takes place. So taking away a few molecules of water or adding a few molecules of water will not change the concentration, or effectively it will not change the value of the equilibrium constant. For that reason, we never included the medium, which is water, which is also a reactant. So in such cases, we do not do that, okay? So if you wrote the equilibrium constant expression Kb for the hydrolysis of acetate ions, the acetate ions would have come from the salt NaC2H3O2. Okay, so that is a sodium acetate that I dissolved in water, of which only the acetate is considered here, and it reacts with water to form undissociated acid plus hydroxide, and the equilibrium constant should look like this. So you will notice something right now. When you write Kb, there will be OH on the equilibrium constant expression. And if you write Ka, which means there should be H3O plus or H plus on the equation. So that is something that you really have to bear in mind. If I write a Kb expression, I'm expecting OH in the product side. When I give you a Ka value, when you write the hydrolysis for that, there will be H3O positive or H plus in the product side. If that is not the case, what you have written is wrong. That is how you deduce whether you've written the right expression or not. Kb expression means the product. So you're writing a Kb expression, the product had water. If you write Ka expression, the product will have H positive or H3O positive. Okay, that is something that has to be true. So pH of basic solutions, so it's very obvious here. A minus plus H2O gives you undissociated HA plus OH minus. Kb can be written, again, when you wrote Kb, you have OH in the product side. Or you can calculate OH minus sign by rearranging the equation. OH minus is equals to Kb into A minus by HA. All I did is rearrange the equation. You need to be able to rearrange equations like this. You have 3 variables on the right and 1 on the left. So it's rearranging. So however you're used to doing it, you should continue doing it the same way. If you have any difficulty, ask me and I can show you. Now, once you have the hydroxide ion concentration, you can determine the pOH of the solution. pOH is equals to negative log OH minus. We have learned that equation yesterday. Or you can calculate pH using the equation pH is equals to 14 minus pOH. So if I give you the concentration of sodium acetate, sodium cyanide, or any salt of weak acid, and ask you to determine the Ka value or the hydroxide ion concentration, or tell me what the pH of the solution is, you should be able to do. A couple of problems that I gave you yesterday involved this kind of hydrolysis. So you had to do this calculation. And that's why I said you may not be able to complete all the questions. So this is a general expression. So from this dissociation, you can write the equilibrium constant expression. You rearrange it to get the hydroxide ion concentration. You can find out the pOH and finally pH. So you can have a problem with numeric values given to you. See, you have learned pH, now you're applying it. You learned equilibrium constant, you're using that. So the concepts are being applied one after the other. These are multi-level problems. So you need to understand the whole concept. If not, you may not be able to connect it. So this correlation between the process, the chemistry that is taking place, and the mathematical interactions that we use to represent them have to be borne in mind while we are trying to solve the problems. Okay? Now we're going to look at hydrolysis of strong conjugate acids. NH4 positive is a strong conjugate acid. Okay, so we had seen earlier, we took this compound NH3 plus HCl will give you NH4 positive plus Cl minus. So this would be the acid, this would be the base. This is conjugate acid, conjugate base. Conjugate base here is Cl minus, so it's a weak conjugate base, therefore no hydrolysis. Okay, this does not undergo hydrolysis. On the other hand, this base is a weak base, therefore this conjugate acid is also considered a strong conjugate acid. Because it's a strong conjugate acid, it will undergo hydrolysis. So we should be able to write a hydrolysis. So strong conjugate acids here can come from compounds like NH4Cl, NH4NO3. All these are different compounds of ammonia, ammonium salts, of which chloride is a weak conjugate base, nitrate is a weak conjugate base. So usually the ammonium alone will undergo hydrolysis and it will change the pH of the solution. Since we already know that strong conjugate bases increase the pH, strong conjugate acids will decrease the pH. That is something that you can relate to right away. Now we also have to write the equation and write the equilibrium constant expression. In this case, it's going to be Ka. And then you can also calculate the pH of the solution. So NH4 positive plus H2O, that is the hydrolysis equation. So in this case, we find that NH4 positive and NH3. If you look at that, the NH4 positive has lost a proton, therefore it's an acid. And this would be the conjugate base. Here, the water molecule actually gained a proton, therefore this would be a base and this would be the conjugate acid. Okay, so you can actually say now ammonium ions are weak acids. That's the reality. And an acidic substance, if you take ammonium chloride and put it in water, because of this interaction, it produces H3O positive that goes up. Therefore, the pH of the solution will go down. The solution is becoming more acidic. That will happen. Okay, so you can actually use this information to actually predict what would happen if ammonium ions are coming from ammonium chloride, ammonium sulfate, ammonium nitrate. It can actually produce a solution that is acidic in nature and the pH will go down. So acidic hydrolysis decreases the pH. That's because it produces hydronium ions. And therefore, this is happening because we have a salt coming from a weak base. That is a relationship that you have to recall while you're explaining it or solving a problem. If you don't see the relationship, the question that you read will make no sense to you. Ammonium ion is a strong conjugate acid. Therefore, it undergoes hydrolysis and the solution becomes more acidic or the pH is lowered. When the hydrogen ion concentration goes up, pH will come down. Bear that in mind. Sometimes while writing an answer, you can make silly mistakes, but it will still cost you mark because you wrote the wrong answer, right? So make sure that you don't make that mistake. So here is the equilibrium constant expression. Why did we put the subscript A? Because we have hydronium ion. So H3O plus or H positive increases the hydrogen ion. That's what we mean by it. So every time you write a Ka expression, you need to have hydronium ions in the product side of the equation, and it comes in the numerator when you write the equilibrium constant expression. So you can rewrite this equation, and you can write it as H3O positive is equals to Ka into NH4 positive divided by NH3. We can also do that, right? And find out the concentration. And once you have that, then you can calculate pH is equals to negative log H positive. You can use this equation, and you can determine the pH of the solution. So if you know the molar concentration, then you should be able to do, or you need to have the Ka value, okay? So this is the equation. This is the equilibrium expression. I just rewrote the equation on the previous slide. H3O positive is equal to Ka into ammonium ions by ammonia. Now, you need to be able to differentiate the names very clearly. This has got a positive charge. The ending is IUM. It is an ion, okay? Here, this is a molecular compound. Therefore, it's called ammonia. The difference should be very clear in your mind. NH3 is a neutral covalent molecule, whereas ammonium ion is an ionic species, okay? That difference is there. Do not confuse between ammonia and ammonium. You will have problems in solving problems and also writing explanation. Yes, that is true all the time. When the strong conjugate base is there, pH will go up, and strong conjugate acid is there, pH will go down. So pH can be calculated from the value once you have the H3O positive. So in order to calculate H3O positive, you will need any two of these, or any three of these values are required. You need Ka, NH4 positive concentration, and ammonia concentration. So those values, if you have, you can solve a problem. So this is the question that I asked in the beginning, qualitative problems, explaining whether the solution will have an increased pH or a decreased pH. So this was the question. I'm rewriting it here. Will adding the following ionic salts to water change the pH of water? NaCl, NH4Cl, NaC2H3O2, and NH4C2H3O2. So what I want you to do is write down for NaCl. Now the answer I want you to type down in the chat is NaCl. Will the pH increase, decrease, remain the same? I would like to have a few. If you do not want to write an answer publicly, you can do a private answer. I'm fine with it. I can still see it. NaCl. The question is, if you're using NaCl, will the pH increase, decrease, or remain the same? I'm looking for answers. I'm looking for more answers. NaCl is a salt of HCl. HCl is a strong acid or a weak acid? So your answer should be based on that. NaCl is a salt that is obtained by a double displacement reaction, which is a neutralization reaction between HCl and NaOH. So HCl is a strong acid, and Cl minus will be a strong conjugate base or a weak conjugate base. Okay, this is HCl is a strong acid. Okay, so if you have a strong acid, then you know that HCl plus H2O, this is the neutralization reaction that produced the salt. That's the equation that I wrote. So this NaCl came from this equation or this product. But HCl plus H2O gives you H3O plus Cl minus. So this is an acid, this is a base, this is conjugate acid, this is conjugate base. The question is Cl minus a conjugate base or a strong conjugate base or a weak conjugate base? The answer should be Cl minus is a weak conjugate base. If Cl minus is a weak conjugate base, will it undergo hydrolysis? So your answer should be Na does not affect because it's a spectator ion. It's coming from a strong base like NaO is. This is a strong base. This is a strong acid, strong base. So Na plus will not undergo hydrolysis. Then we are looking at Cl, which is a weak conjugate base because it's coming from a strong acid like HCl. Therefore, weak conjugate bases do not undergo hydrolysis. Therefore, no change in pH. So if you put NaCl in water, there is no change in pH. If not, you would have actually felt it. Every time you put some table salt in water and drink it, you will know if it's changed its pH. If the pH went up, the solution will turn slightly bitter. If the pH went down, the solution will turn sour. Acids are sour to the taste, bases are bitter. Haven't you learned that in grade 9 and 10? Properties of acids and bases. So if you are drinking table salt, it should have been. But we have a salty feeling to it. That's a different feeling altogether. So it's neither an acid or a base. It does not change the pH. So that's the way you explain this. So we are trying to explain the question that I asked you at the beginning of this lesson. So I want you to take a moment and tell me, I'm not going to do any explanation. If I add NH4Cl, what would be your answer? I've actually just explained everything in the previous slide, so you should have an answer for that. NH4Cl. Now, one thing we established, Cl minus does not contribute to changing pH because it's a weak conjugate base. Now, you have ammonium ions in it, so this will dissociate to give you NH4 positive AQ plus Cl minus AQ. So you have to consider each of them. This is a weak conjugate base. What about this acid? It's a strong conjugate acid. If it's a strong conjugate acid, it should or should not undergo hydrolysis. So what would be the answer? Would the pH go up or come down, or would it remain the same? If you can type in your answers. The question is, will the pH go up or come down? Because the pH will come down because NH4 positive is a, you also need to correlate it. It will go down, that is correct, is a strong conjugate acid. Therefore, there will be hydrolysis. The answer should be NH4 positive is a strong conjugate acid. Therefore, it will undergo hydrolysis. And then you can write the equation for hydrolysis. NH4 positive plus H2O reversibly gives you H3O positive AQ plus NH3. So in this case, the H3O positive went up, therefore pH will go down. So you should be able to write an equation for this, and you should be able to make the prediction. NH4Cl comes from a strong acid. NH4Cl because the acid is strong because HCl was used. But what about the base that was used for preparing ammonium chloride? We used a weak base, ammonia, or we use ammonium hydroxide, and that is a weak base. So the positive ion, NH4 positive, which was a conjugate acid, came from a weak base. Therefore, it's considered to be a strong conjugate acid. Okay. I want you to write something in your notebook as to what you understood. And then if you still have a question, ask me. I know there are more than one concept being applied at the same time. If you don't see how we are doing it right now, it'll be difficult later. So I want you to take a moment, see if you can write the answer by yourself. And if you still feel that you have something not clear, ask me now. I'm going to give you 2 minutes to ask me a question. So did you write an answer, and did you write your own little notes for the explanation why the pH goes down for NH4Cl? NH4 positive is a strong conjugate acid. It's coming from a weak base like ammonium hydroxide. And the acid used for neutralization to prepare ammonium chloride is HCl because we have Cl minus. And the base used was NH4OH that produced ammonium chloride and water. Then we are looking at NH4 positive, which is a strong conjugate base. Strong conjugate bases can undergo hydrolysis, and we can write a reaction for that. Okay, that's because you missed the first part of the lesson. So this is how it goes. I gave you a list of acids, right? HCl, HBr, HI. That is the halogen acids. Then you have HNO3, HClO4, and H2SO4. These 6 acids you got to memorize. All of these negative ions over here, which is chloride, bromide, iodide, nitrate, perchlorate, and sulfate, they are all weak conjugate bases. Any other negative ion, we're going to say is a strong conjugate base. That's how you determine it. Does it make sense? So use that information. So in this case, Cl is over here. Therefore, it's a weak conjugate base, no hydrolysis. In the first case, Cl, coming from Cl, it's a weak conjugate base, therefore no hydrolysis. Now, this pH change for the second example is coming from the first part, the positive ion. So if a positive ion can undergo hydrolysis, then the pH will go down. So in this case, it's ammonium ions. Ammonium ions are coming from ammonium hydroxide, which is a weak base. Therefore, the pH will go down. So the third example, okay, the third example, this is sodium acetate. Now you should recognize the formula. This is sodium acetate. If I replace the sodium with hydrogen, it changes to HC2H3O2, and that is acetic acid. So this is a negative ion. This negative ion, is it present in this list? You do not find it there. So what kind of base is it? Strong conjugate base or a weak conjugate base? Can you type your answer in there? It's a weak conjugate base. If it's a weak conjugate base, will it undergo hydrolysis? Oh, I mean, it's a strong conjugate base. Sorry, my mistake. What you're referring, Ryan, is coming from a weak acid. But the salt, the negative ion that comes from a weak acid is always considered a strong conjugate base. The acetate ion is not present in this list. If you look at this list, you'll find acetate ions are not there. So when you dissociate this in water, it changes into Na plus C2H3O2 minus. This negative ion is not in this list. Therefore, it's a strong conjugate base. All of these are weak conjugate bases. Therefore, a strong conjugate base will undergo hydrolysis. Okay, so you should be able to write this equation: C2H3O2 minus plus H2O, reversibly giving you undissociated HC2H3O2, which is this compound, plus OH, because this hydrogen is coming from HOH. It takes the hydrogen from here, and what remains is the OH minus. Therefore, the pH will go up. I mean, the hydroxide ion will go up, and the pH will also go up. Does it make sense? There are videos posted explaining all of this there under hydrolysis. All of this information is posted there. A lot of videos are posted. My own videos are posted there, so check that out. If you still have questions, you should ask me. That's the whole point. The last one is a little bit tricky, okay? So the first 3 has been explained. If you still have questions, don't hesitate to ask. I don't expect you to totally understand it. You can have doubts when we discuss more and more examples. So for that reason, if you feel that you have something that is not clarified in your mind, don't hesitate to ask. I expect you to ask questions here. This is a totally new topic, and this can have more than one stage of explaining. For that reason, you can find it a little bit challenging in the beginning, but once you understand it, it's not very difficult. So now I want you to look at this example, okay? NH4 C. So if you dissociate this, changes into NH4 positive plus C2 H3O2 negative. So I want you to make a guess and tell me, will the solution have a change in pH? Will the pH increase or will the pH decrease? It's an interesting question, but you may have, a lot of you may have half to 3/4 of the answer. That's good enough for me at this point of time. But the last part, if you can reason it out, is good. But if you can tell me what would happen, because when you dissociate ammonium acetate in water, it gives you ammonium ions and gives you acetate ions. You had done second example and you had done the third example. So the last one is a combination of both. So this finally, will the solution be more acidic or more basic? That is the question. The statement is right. They are both, you have a strong conjugate acid. This is a strong conjugate acid. Therefore, it will undergo hydrolysis. Yes, here, this is a strong conjugate base, and therefore it will undergo hydrolysis. Yes. So the question is, now you have to give me a reason if you say which is more acidic or more basic. Both of them undergoes hydrolysis. We have proved them from this equation, this example and this example. In ammonium chloride, the pH went down. In sodium acetate, the pH went up. So we have ammonium ions, which can cause the pH to go down. We have acetate ions, which can cause the pH to go up. The question is, will the solution finally be acidic or basic? Any more thoughts on it? If anybody wants to make an educated guess, it's fine. I don't expect the right answer, but at least the reasoning behind it is something that you can actually talk about. If you have any possible answers, write it down, it's okay. If you say more acidic, you need to have a reason for it. You have to state what that reason is. Okay, let's do. I'm going to write the hydrolysis for both of them. And then we will see what we can do, okay? So for ammonium ions, I'm going to write an hydrolysis equation. NH4 positive plus H2O, reversibly giving you H3O positive plus NH3. These are the two products that I get, okay? So for this dissociation, I can write what we call an equilibrium constant expression. I'm going to write Ka, because this has hydronium ions. That's going to be products over reactants, H3O plus into NH3 divided by NH4 positive. Similarly, that's for ammonium ion. Now for the acetate ions, I can write an equation similar to that. C2H3O2 plus H2O gives you undissociated HC2H3O2 plus OH minus. So this is AQ, okay? Now I can write, because there is OH minus, I can write an equilibrium constant expression, and that is going to be KB. That's what I have. So now I have a value for Ka and I have a value for Kb. If the value of Ka is equals to Kb, what will be your answer? If the value of Ka is equals to value of Kb, what is the answer? Anybody? If the value of Ka and value of Kb is the same, if they are both equal, what would happen to the pH of the solution? Will it increase, decrease, remain the same? That is, the numerical value of Ka and Kb are the same. Then the pH will remain same, because the hydrogen ion increase by ammonia is neutralized by the hydroxide ion formed by acetate ions. So this is what would happen. The final answer depends upon whether Ka is larger or Kb is larger. If Ka is greater than Kb, pH will go down. If Kb is greater than Ka, pH will go up. Does it make sense? So the value of Ka and Kb will determine whether the solution is acidic or basic. Because if the solution, if the Ka and Kb are the same, in this case, they're not the same, and I don't remember the values, but this is the way. I may give you an example which is not known to you, but you can have the Ka and Kb values calculated by some means. Then your explanation will depend upon whether the Ka is larger or smaller for the given examples. Then that's the important thing. So if you are given an ionic compound where both the cation and the anion can undergo hydrolysis, Ka and Kb will determine whether the solution is acidic or basic. Okay. So this is a qualitative, which means there is no calculation involved. We are merely looking at the ability of an ion to undergo hydrolysis based on whether they are strong conjugate acids or strong conjugate bases. That's what we did here. Okay. Now there will be quantitative examples. That is actually some of the things that were given to you in the earlier worksheet. So it's again an explanation. NaCl in salt is a salt of the strong acid HCl and the strong base NaOH, neutralization. And this is the equation, and Cl minus is a weak conjugate base. This is what you should be writing. Therefore, since Cl minus is a weak conjugate base, it does not undergo hydrolysis, no change in pH. Okay. Na positive comes from a strong base, so it's a weak conjugate acid. They are spectator ions usually. They do not actually cause hydrolysis. But metals like aluminum, iron, transition metals with high positive charges, they can undergo hydrolysis. So just to have a general understanding, if I take ammonium salts, ammonium nitrate, aluminum nitrate, aluminum can undergo hydrolysis. If I give you ferric nitrate, if I pour it in water, put it in water, it can undergo hydrolysis because Fe3 plus high positive charge. So metals or transition metals with very high positive charges, if they are present in the ionic compound, they can undergo acid hydrolysis. Okay. Again, the explanation, what I would expect you to write, NH4Cl is a salt of a strong acid HCl and a weak base ammonium hydroxide. And if I take NH4 positive, it can undergo hydrolysis because it is a strong conjugate acid, gives you conjugate acid and a conjugate base. In this case, the hydronium ion is going up. This is going up. So this is going up. So Cl minus is a weak conjugate base. Therefore, Cl minus does not undergo hydrolysis. NH4 positive is a strong conjugate acid. Therefore, it undergoes hydrolysis and causes the pH to go down because it's a strong conjugate acid. Okay. No, not typically a concentration quotient. The Ka and Kb value, the absolute values. The last example, the third example that I gave you, NaC2H3O2 is the salt of a weak acid. Acetic acid is a strong and a strong base. Okay, so the weak acid is acetic acid. So NaC2H3 is a salt of a weak acid like acetic acid and a strong base. So acetate ions are strong conjugate bases, reacts with water, produces undissociated acids, and increases the OH minus. This goes up, pH goes up. Okay. So C2H3O2 is a strong conjugate base. It undergoes hydrolysis. Na positive is a weak conjugate acid, does not undergo hydrolysis. The solution becomes more basic because of the hydrolysis of the acetate ions. Okay, so this is the answer expected when you're asked a question like this. So you can be very precise about what you're writing. I hope you understood the reasoning behind what we have done. Again, the last example, ammonium acetate is a salt of a weak acid, that is acetic acid, and a weak base, ammonium hydroxide, therefore, has both strong conjugate base and strong conjugate acid. So acetate ions, like we already said, produces hydroxide ions, the previous slide. Ammonium ions react with water, produces hydronium ions, therefore increases the pH, increases the hydronium ion concentration. Therefore, since it is a strong conjugate base and a strong conjugate acid, the pH will increase for the strong conjugate base and pH will decrease for the strong conjugate acid. So the question is, will the solution become acidic or basic? What determines this aspect? That's what we explained. If we know the Ka and Kb value for this equation, you will write the Kb for this equation and you will write the Ka, or the numerical values have to be given to you. If you have those values, you can say whether the solution will be acidic or basic by comparing it. Whichever has got a larger value, that will determine the pH of the solution. If Ka is larger, solution will be acidic. If Kb is larger, solution will be basic. Okay. So the pH of the solution in this case depends on the Ka value. If Ka is greater than Kb, then the solution is acidic and vice versa. So you can actually go and check out the values for Ka and Kb for ammonium ions and acetate ions and then figure out what should be the right answer. Okay. So that's regarding hydrolysis, and some of the problems that you had to use this hydrolysis equation to calculate it in order to obtain the solution to it.